Hello, Dean, KK4DAS here. Welcome to this edition of the SolderSmoke Challenge Direct Conversion Receiver. Today we're going to talk about the diode ring mixer and diplexer board. Hey, if you haven't already done so, please subscribe to the channel and click like on the video and share it with your fellow hams and club members. It really helps get the word out on Homebrew Ham Radio. So today we're going to be talking about the mixer. And if you recall, our receiver has four boards. It has the oscillator, which we built, hopefully built, over the past week. I know some of you built it. I've seen the videos, and we've had a lot of discussion about the oscillator on our Discord channel. We have the bandpass filter, which was going to put us in the 40-meter band, and we have the audio amplifier, which is going to produce the audio out to the speaker. But today, we're going to talk about the mixer, and the mixer is the heart of a direct conversion receiver. It's the thing that makes it a direct conversion receiver because it's the part that takes the filtered RF signal, combines it with the oscillator, and out of that comes audio, which we can then amplify and play through the speaker. Recall what a direct conversion receiver is. This receiver takes radio waves in at about 7 megahertz, so on our 40-meter band. Of course, we can't hear RF. We need to hear audio, so we need to convert that down to RF, and that's or to audio rather, and that's roughly 300 hertz to 3 kilohertz. So we convert them to sound waves that we can hear. We do it in one step. That's called direct conversion. The mixer does the conversion for us. That's why the mixer is so important. So here's the example. Our antenna signals are coming in at 7,200, 7.201 megahertz. So your dial's tuned to 7,200 and you're talking and your audio is up above there. Your oscillator is set to 7,200. The sum frequency is 14,401 megahertz. That's radio frequency. We can't hear it, but your receiver can. The difference frequency is 1 kilohertz or audio frequency. So we take the difference frequency, we amplify it, we listen to it. We just get rid of, discard, filter the sum frequency. That's the essence of mixing. That's what this receiver does. There are lots of types of mixers. We're going to be dealing with a passive diode mixer, but even within passive diode mixers, there are unbalanced mixers, single balanced mixers, and double balanced mixers. So why did we pick double balanced mixers? Well, we tested a bunch of different configurations, and we found that the double balanced mixer worked well in this direct conversion receiver. It gave us good audio, kept a fair amount of the unwanted signals out of the audio. And then, the rationale for a double balanced mixer is that it has increased linearity. Compared to the single balance mixer, the ports are isolated from each other, although there can be some leakage of LO through to the IF port. And it's done with passive elements, no biasing, and it's inherently broadband. So it'll work for RF, and it'll also work for audio. And it'll, particularly our case, it helps us mix down from RF to audio. Now, there's other kinds of mixers. There are transistor switching mixers. The Gilbert cell is one of those. There are active MOSFET mixers that mix and amplify. There's a variety of commercial ICs that implement various kinds of mixers. But in keeping with the spirit of the SolderSmoke Challenge, we chose to go with a simple, discrete component diode ring mixer, double balanced diode ring mixer. All right, let's take a look at the schematic. It's very simple. There are 4 diodes and 2 transformers. That's it. That's the entire mixer. And then the audio diplexer is a secondary circuit that we're going to put on the same board. Now, when you look at a schematic of a transformer, you're going to notice a couple of things. One is hopefully the person that drew the schematic will tell you something about what they have in mind. So you see the blue text, 10 trifilar turns on an FT50-43. That's pretty important because it's the number of turns and the type of and size of toroid that you use that determine the frequency and frequency response of the transformer. So it's pretty important to know what they have in mind. You'll notice that if we look at L5, 6, and 7 on the left, that we have the inductance listed, 33 microhenry. Well, that pretty much tells you that all three windings are going to have the same number of turns. So that's pretty helpful. And it's the inductance and the ferrite mix or the toroid mix that it determines the number of windings that you need. So we've tried to provide as much information as you can. You'll also notice that there are little dots next to the L5, L6, and L7. Those are really important. Those are phase dots, and they indicate the phase of the winding. They also show us how we would interconnect the windings, and this is going to be important as we wind those toroids and solder them up. The way I like to think about it is if you're holding the transformer vertically and you have all three wires round around there 10 times, you've got 3 windings sticking out at the top and 3 sticking out at the bottom. The ones on the top are going to be the dots, and the ones on the bottom are going to be where there are no dots. So if you look at the schematic, you can see that the bottom of L5 is going to be connected to the top of L6, and that junction of that connection is going to be grounded, and that is how you read the schematic of a transformer of this sort. Another thing to note: take a look at the way the diodes are interconnected. It's called a diode ring because they're all in a ring like a cat chasing its tail, cathodes connected to anodes all the way around. And if you get one of those diodes wrong or 2 of them wrong, you will have a different circuit and it won't do what you want. The transformers are identical. They're just wired slightly differently. And you'll note that the mixer is a 3-port device. It takes RF in, and it takes a local oscillator in, and it produces audio frequency, or what we call the intermediate frequency, out. A couple other things on the schematic to note: those numbers K1, L5, L6, L7, those are directives for LT Spice, which this was drawn in, that will allow you to actually simulate this circuit in the LT Spice program. You don't need those, and you don't need to know what they are for the purposes of building this mixer. Now, if the mixer produces audio out, what do we need this thing called an audio diplexer for? Well, strictly speaking, for the receiver to operate, you don't need it. You could go straight from the AF out into the audio amplifier. And in fact, our first build we did that, but we found that we had some stray mixing products getting through to audio. We had some AM broadcast breakthrough. We got a very, very loud nearby Spanish language station called Radio Marti just down the road, and I was hearing it so frequently that I was getting ready to invade Cuba. That's a line from Bill. Anyway, so what does the diplexer do for us? It provides termination to a 50 ohm termination to the frequencies coming out of the mixer. And I said, well, you said audio is coming out of the mixer, so what are we worried about? Well, not only is audio coming out of the mixer, but remember, it's producing a sum and a difference and a whole bunch of harmonics. So there's a whole bunch of different sine waves that come out of that mixer, and that C7 and R7 make sure that the high frequency ones are shunted to ground, and they present a 50 ohm termination. The 100 microhenry inductor and the 0.47 microfarad cap form a low-pass filter with a cutoff at 23 kilohertz. All of these things help kind of get junk out of keep junk out of the audio amplifier, which is what we're going to build, right at the end. So that's it. That's the diode ring mixer and the audio diplexer. I'll give you a little more discussion on this mixer. First, I want to address a couple of what I'm calling myths, legends, lore, and truth. And there's probably as many myths, legends, and lore about mixers as there are about antennas, if you can believe that or not. So the first myth is you need 7 dBm or 10 dBm or name your dBm to drive a diode ring mixer. That is a myth. You need enough voltage to turn the diodes on and off, and the mixer will mix. These are switching mixers, and as long as your LO is stronger than your RF and provides enough forward voltage to turn the diodes on and off, your mixer will mix. You may get more or less intermodulation distortion. You may get more or less harmonic products out, but it will mix. And we're not providing 7 dBm to the mixer, and it mixes just fine and produces really nice audio, as you've seen if you watch some of the videos. Next one, you must provide 50 ohm termination to all 3 ports of the mixer. Well, there's another legend. It may have less loss. There may be fewer harmonics if all ports are terminated in 50 ohms, but it is absolutely not required for mixing. In fact, we didn't terminate it in 50 ohms in our first build, and it worked. Next one, and this gets into a bunch of comments that have been popping up on the Discord chat. You must or can't use a simple silicon diode, or you name your favorite diode. None of that is true. Virtually any small diode will work in a diode ring. Could be a silicon junction, Schottky barrier diode, gallium arsenide. Pretty much any diode will work. They may have slightly different performance characteristics, but really they will work. Last one, any nonlinear circuit, even a single diode will mix. Yep, that is it. Nonlinear switches are great mixers, and there was some comments on the Discord server about whether or not the diodes are actually switching. They absolutely are switching diodes, and that is required in order for the mixer to do its job. So if you want to learn more on exactly how a mixer works, I highly recommend that you go to Alan Wolke W2AEW's YouTube channel and watch his series on diode ring mixers. His YouTube video number 167 in particular is really informative, and it explains exactly how these mixers work, and you'll come away with a much better understanding of how a mixer does its job than I can give you here. Alan is a fantastic electronics teacher, and not only that, I recommend you watch any of the other videos on his channel. They're all very informative, and I go back to them over and over again. Also, our friend and colleague Bill, N2CQR, you could say he has a slight obsession with mixers. He explains how our diode ring mixer on the SolderSmoke blog, and you know, if you just search mixers on his blog, you'll come up with 15 or 16 posts over the year. All right, so that's it for the intro. Let's get into looking at how we build the diode ring mixer and Diplexer. For the diode ring mixer, I decided to go ahead and use the Me pads from Rex and show you kind of they work just as well as the homemade pads. I've already glued them on the board in the right orientation that I want them. I've marked where the local oscillator port, the RF port, and the AF port are going to go. Those are just, reminders to me. You don't need to necessarily mark your board up like this, but this kind of shows you what you're looking for. Now, when we did this for the high school students, I did a very detailed step-by-step guide for them to put these together, because this is one of the stages that it's easy to make a mistake. You've got all of these windings on the toroids that are in different places, and it's just easy to get it wrong. So being organized really helps. You can download that off the Hackaday site. Now, as we've seen, the purpose of the mixer is to take radio frequency coming in from the antenna, local oscillator coming in from the PTO, and mix those together and produce an audio frequency output. Then from the audio frequency output, we're going to pass it through a diplexer to make sure that the mixer sees 50 ohms and that the following stage gets 50 ohms as well. So that's what we're going to build. It's a very simple device, just 4 diodes arranged in a ring. As we talked about a minute ago, the diodes have got to be back-to-back, cathode to anode. all the way around in a circle, as opposed to a rectifier, which has a different architecture, although they look the same. The input and output transformers are wound on T50-43 toroids, mix 43, and they're tri-filar wound, and we're going to look at how to do that in just a minute. You need 3 pieces of magnet wire, each about 9 to 10 inches long, to wind on these toroids, and I'm going to show you how we do that and wire the transformers up. Tri-filar transformers can be a little tricky because you've got the 3 windings and they have to be connected in just a certain way, and this is one of the areas where people often make a mistake, so take some time and be careful. Now you'll notice I have 3 different colors wires. I have a red, a green, and a copper wire. That'll make it easy for me to keep the windings separate. But even if you don't have that, you just need to take some care that you know which winding is which, and you can use a multimeter to buzz them out. So the first thing we're going to do is we're going to take the 3 wires and we're going to twist them together until they have about 8 to 10 turns per inch. And what I'm going to do is I've just got a little eye hook here. I'm going to wind a couple of the ends in there and twist it around, and then I've got a hand drill that I'm going to use and just clamp them in the vise, and I'm going to make about 8 to 10 turns per inch of the wires. So let me do that and then I'll be back. So I've completed winding the wire. I've got about I don't know, 8 to 10 twists per inch. All 3 wires are wound together. Now I just need to wind them on the toroids, and go back to the schematic. You'll see we say 10 tri-filar turns on FT50-43. So I'm going to pass the pass one end through, and that constitutes 1 turn. And every time you pass the wire through the center, that constitutes a turn. So I've already got 1. That makes 2. And you pull it fairly tight. And that makes 3. So I now have 10 turns on each of the toroids. The toroids are wired identical. They're exactly the same for both of them. On this one I've separated the copper, red, and green. So I have copper, red, and green on top, copper, red, and green on bottom. I'm going to call those windings 1, 2, and 3. 1, 2, and 3. I've got the top of 1 and the bottom of 1, top of 2, bottom of 2, top of 3, bottom of 3. Winding 1, we're going to leave alone. We're not going to do anything with that at all at the moment. We're going to take the top of winding 2 and we're going to connect it to the bottom of winding 3. So the top of the red goes to the bottom of the green. That's going to be our transformer tap point. So those I'm just going to twist together and get them out of the way there. I'm going to twist those together right now so that I know that that's my tap point. And then I'm going to solder those together. So I took the top of the red to the bottom of the green, the top of winding 2 to the bottom of winding 3, and again winding 1 we are not going to do anything with at this point. So now I'm going to remove the enamel from those 2 like I showed in the previous video. Then I'm going to solder those together, and that's going to make our tap point. And I'm going to do the same thing on this toroid, and then the toroids I'll also remove the enamel and tin all the wires, so both toroids will be wound, transformers will be wound and ready to go. So again, leave winding 1 alone, take the top of winding 2, connect it to the bottom of winding 3, and that will prepare your toroid for mounting on the board. Okay, the transformers are all prepared. They're prepared identically. I've soldered the tap points together. I've cleaned and tinned all the leads so they're ready to solder down to the board, and we're going to set those aside for now. Next, we're going to do the diode ring. Now, the diodes, whether you're using these Schottky diodes or the 1N4, 1/4, they all have the cathode marked with a line. And we're making these in a ring, so it's really important that you get the cathodes and the anodes connected to each other, so they go just like that. So I'm going to prep the first one and put it down and show you what that looks like. So there's the first diode soldered down, and I'm using the same kind of upright technique I used with the components on the yellow board. It works really well for this. You can lay them flat, you just need to spread the pads out a little bit further, but this will work fine. So now I'm going to go through and put the other 3 diodes in. Alright, I have all 4 diodes soldered in, and very carefully looking that they go from cathode to anode, from cathode to anode, from cathode to anode, all the way around. I'll let you in on a little secret. I soldered one of them in backwards, and when I was doing the QA check, I discovered and I had to reverse it. But they're all correct now, and they're all in the right place. So the next thing to do is to put the transformers on. Okay, so we're ready to solder in the first transformer. The tap on this transformer goes to ground, and on the primary, which is winding 1, or the copper winding in my case, one end goes to the input and the other end goes to ground. The winding 2 and winding 3, one goes to the top pad over here and one goes to the bottom pad over here. So tap goes to ground, winding 1 goes from the local oscillator to ground, top and bottom. The other 2 windings go to the top and bottom pad. The first transformer is in, and I did shorten the leads a little bit, but if you do that, make sure you get the enamel off and get them tinned before you solder them down. So again, we've got winding 1, or the primary, that goes from the input to ground. The tap of the center conductors, or the 2 that are twisted, goes to ground, and then one goes to the top pad and the other goes to the bottom pad. All right, for the output transformer, we're going to take the output from the tap. So the tap is going to go to the RF port, or the AF port, rather, the audio out port. The RF is going to come in, and just like on this side, we're going to use winding 1. One side is going to go to the pad and one side is going to go to the ground. And then one of our windings is going to go all the way across to this pad over here. So you have to be careful because that's going to cross across. You don't want to short things. And then the other is going to go to the nearby pad. And so I'm going to put that transformer on the board right now, and we'll take another look. So both transformers are in. I've taken care to keep the leads relatively short. I've made sure that I've got good solder joints, that there's no cold solder joints, that all the leads are tight. I've taken care to make sure that none of the leads are shorted to each other, that things go where they're supposed to go, and there's no bare wires touching where they're not. So, as I mentioned at the beginning, this board is probably the most difficult board to build properly, and so you just need to take your time. There's not a lot of parts, but the wiring is sensitive. The toroids need to be wound exactly right. The leads need to be connected to the right ports. The diodes need to be back to back. All the leads need to be soldered well with no cold solder joints. So next thing I'm going to do is I'm going to put some little test points on each of the ports, and we'll test the mixer, and we'll take a look at what it looks like. The mixer is built and it's time for testing. And here's how I'm setting up a test. I have a signal generator. I have the local oscillator circuit set up for exactly 7 megahertz at 2 volts peak to peak. And I have the RF signal at 7 megahertz and 1 kilohertz at 0.2 volts peak to peak. And that's what I'm going to use to drive the mixer. I have the mixer here. So the LO is coming in over here, the RF is coming in over here, and then the AF output, the audio frequency output, is being measured on the oscilloscope. And I've got the oscilloscope set up in its spectrum analyzer fast Fourier transform mode. We're at a 1 millisecond sweep rate. I have the center at 1 kilohertz with 5 kilohertz divisions. And so the peak you're seeing there is the 1 kilohertz audio tone that's coming out of the mixer. Now, there's also a 14 megahertz tone, but it's way off to the right on the screen and you're not going to see it here. But the point is, the mixer is taking the RF and the LO and stripping out the audio and producing the audio. And that's the signal that is going to be fed to the audio amplifier stage. With the mixer built and tested, it's now time to add the Diplexer circuit, and that's just 4 more components. We're going to run a 100 microhenry inductor from the AF output to this pad over here. These two components here, the 0.1 microfarad and the 50 ohm resistor, are going to come right off of the AF port to ground, and that's going to provide 50 ohm termination to the mixer. Mixer ports like 50 ohm termination. And then the combination of the 100 microhenry and the 0.47 microfarad cap are going to give us some low-pass filtering, so that we're basically only sending audio onto the audio amplifier. I don't have a pad for this junction right here. I'm just going to solder one end of the cap to the other end of the resistor and just put it in as a single component at that point. So I'm going to solder that up, let you see what that looks like, and then we'll connect it up to the LO and we'll do another test. I've completed assembling the Diplexer circuit. There's the 0.1 cap tied to the 50 ohm resistor to ground. There's the 100 millihenry inductor, and then there's the 0.47 microfarad cap to ground. I'm not going to use this pad. I thought I was going to use it earlier, but I decided not to. Now, in order to test this, I want to put the output capacitor on there, which is the coupling capacitor to the next stage, which is, if you look at the audio amplifier circuit, it's a 33 microfarad cap. I only have a 47, so that's what I'm going to put in there. There's another one of those cases where the exact value isn't all that critical. It's going to affect how much of the highs and lows you get in the audio, but the 47 should work as well as the 33. But let's solder it in, and then we'll do another test. Just a quick double check on the Diplexer circuit to make sure nothing has gotten screwed up. Same test as before, and same results as before, except you'll see the sine wave looks a little cleaner at the top. That's because of the filtering. And for another look at the signal coming out of the Diplexer circuit, there is our 1 kilohertz audio tone. I've now soldered the two boards together. I put a little jumper between the output of the PTO and the LO, and very importantly, I put a piece of solder wick, solder braid, to ground the two boards together. It's really important in these RF circuits to have all of your boards grounded at the same ground potential. Now, the beauty of building in modules the way we do and testing each module separately and then putting them together is it increases the likelihood that when you put them together, the final circuit is going to work. So let's try it out. So what we're going to do is, I've already gotten rid of the LO from the signal generator. I've changed the RF frequency to 7.201 megahertz. And I know already from our previous test that I'm right around 7.2 on this PTO. And I've got the scope all set up and ready to go. So what I'm going to do, see if I can get all this in the frame at the same time. I'm going to turn the PTO on. All right, we already have some kind of signal coming through the mixer, but let's see if we can find our 7.201. Just all I'm doing is gradually tuning. Let's see what happens here. Oh, we're getting there. All right, there's our signal. There is our signal. Our receiver, this is now a receiver, is working. We have a local oscillator and we have an RF signal, and we are producing an audio signal. So we are in good shape, folks, for the rest of this build. So this is Dean, KK4DAS, signing out, and I'll see you next time.